Greetings, Crazy Eights. Hopefully you had a wonderful snow day yesterday, or wind chill day, or whatever you want to call that. I personally was very, very sad that I was unable to see some of the favorite people I have, my students. I needed a lot of consoling. Why? Get over it. Anyway, there's two main concepts that I want you guys to be able to understand that I wanted to teach you yesterday, but instead I'm going to try to teach those to you and have you learn those through this video and through a blog response. So the first thing that I want you guys to know about is how geologists and seismologists, earthquake scientists, can locate the epicenter of an earthquake. We see it all the time, and they can pinpoint the exact location of those. I want you guys to know how to use the SP lag time method to be able to do that. It uses waves that earthquakes cause. P waves and S waves, two waves that we know already. P waves are the fast ones. They travel faster than the S waves, and the S waves, of course, travel slightly slower. And that's consistent. Scientists know how fast P waves travel through certain things. They know how fast S waves travel. If they are able to get a reading from those waves anywhere in the world and calculate the distance between the arrival of the P wave and the arrival of the S wave, they can calculate exactly how far that seismograph station is away. You might want to think about it like this. The P wave is faster. It continues to travel faster. So let's say we start with a P wave and S wave. They originate in the same spot, the epicenter. Now the P wave is fast, kind of like, think of somebody really fast, like me, Mr. Hoig. And then think about someone that is slower, somebody like Kyle Ollinger. I kid Kyle because you're a pretty fast dude. But anyway, for this example, I'm going to be the fast wave, the P wave. Kyle will be the S wave. The longer our race goes, it starts at the epicenter, the longer it goes, the P wave continues to travel faster. And as time goes on, the distance in between the P wave and the S wave increases. Scientists can measure the distance between the P wave arrival and the S wave arrival, and they measure that in seconds, and then they can figure out exactly how far away the epicenter of an earthquake is. Maybe I'll show you something else to demonstrate that too. This might be a pretty good visual that you can use to know how P waves travel faster than S waves. When the earthquake starts here, notice how the P wave and S wave are together. The longer it goes, the further the distance between the P wave and the S wave gets. Now scientists can measure from the start of the P wave to the start of the S wave. That's the SP lag time, just like this tutorial shows. They can calculate the exact distance that seismograph station is from the epicenter. Here's an example of a seismograph reading that you might see called a seismogram. That's what it would be called. Here is the P wave, and over here is the S wave. To calculate the SP lag time, you would measure from the start of the P wave to the start of the S wave in seconds. Once you've done that, you can pinpoint the location, or at least the distance away that this seismograph is from the epicenter of an earthquake. The further the distance is between the P wave and S wave, the further that seismograph station is away. Let's say that SP lag time that we just measured came from a seismograph station in Bismarck. We could then use a graph to detail how far away that earthquake's epicenter is. So let's say it's about that far away from Bismarck. That's not enough to exactly pinpoint the location of an earthquake. It could be anywhere along this circle, but we do know it's this far away from Bismarck. We need more information than from just one seismograph station. But let's say there's another seismograph station in Salt Lake City, and by measuring SP lag time, they are able to find out how far away that earthquake is from Salt Lake City. This is still not enough. It could be one of two places. It could be the epicenter could originate here, or it could originate there. You would actually need 3 different seismograph stations to know where exactly the earthquake is. Now, let's say there's a seismograph station here in Austin. Hopefully the Longhorns won last night. Anyway, maybe there's a seismograph station in Austin, and you find that it's exactly this far away from Austin. And that should intersect at a certain point. So now we know exactly where the epicenter of this earthquake happened. And that's all. The second concept that I want you guys to understand a little bit about is the different fault types that are created and that cause earthquakes, volcanoes, etc. There's 3 main fault types that I want you to know, and they're very similar to what we have learned about the 3 different types of plate boundaries: convergent, divergent, and transform. See if you can find the relationship between plate boundaries and these 3 different fault types. It should come pretty quickly for you. The one that you see in this picture is a normal fault. One thing to notice is that it's similar to a divergent boundary. Look at the arrows on the right and left in blue. They're going away from each other, and normal faults are really just like divergent boundaries, where you have this footwall on this side and the hanging wall that slopes like this on the right side, and it goes the way you would expect it to normally. This footwall or this hanging wall slides down as the arrows show down the slope. And this happens when there is a divergent boundary. You would expect to find normal faults like this one. The next type of fault that you might expect to find along plate boundaries is a reverse fault. Not a normal fault, but a reverse fault. And in this case, these arrows are pointing toward each other, which tells you this would happen in a convergent boundary with 2 plates colliding. The reverse fault is the opposite of the normal fault. This hanging wall now goes up in relation to the footwall on the left side. So this is a reverse fault. The third type of fault line that you might expect to find along plate boundaries is a strike-slip fault. A strike-slip fault is very similar to a transform boundary. So we've really covered the 3 types of plate boundaries with these faults. The strike-slip fault is when 2 different plates are sliding past one another, just like a transform boundary. That should be it for the video lessons. Good luck on your blog responses today. Remember to be complete and thorough with all your answers, and good luck with the Adiskio